Hi, everyone. This is the first video segment of Chapter 5, Section 5. I just want to say at the very beginning, there's a lot of material in 5.5, surprisingly, because there aren't a whole lot of new ideas going on here. And rather than try to cover every single thing that pops up in here, there's a whole class of identities that I am just simply going to ignore. They don't have a whole lot of utility for us, and you may see them in a Calc 2 class. It's probably about the only place you'd ever see this sort of trick. And I mean, it's unfortunate, but I think that at some level we should start deciding what's more important to cover. I'm still debating on that. I mean, it would be relatively quick, but there isn't a whole, I mean, there's not a whole lot of utility that I can point out right now. And so, you know, it's something that maybe is not all that important. But the stuff that is important is the so-called double angle identities. Really quite useful. You know, last time we had talked about ways of manipulating the arguments of trig functions to produce different identities that maybe had some value, and now we're really starting to work inside the arguments here. There are what are called these so-called double angle identities, but you can extend this to triple, quadruple, whatever else. I mean, once we figure out how to, you know, double an angle from a functional standpoint, the next step would be to divide an angle, and then we can achieve any sort of between those two, we can do all kinds of algebraic manipulation inside of the argument, because we already know how to add and subtract. You know, so now we're trying to develop multiplication and division. We don't really get that far down that road, but it does show us some interesting behavior. So what we're going to do is first, and I'll probably just do it on this segment, is that I'm going to derive the double angle identities for sine, cosine. There's actually 3 of them for cosine, and then tangent of a double angle. And then I'll probably come back with later segments to reinforce it, some practice problems, and kind of give you some idea of how to approach those. Okay, so with no further ado, I'm going to shift over here. I haven't checked my visual settings for a minute. I think it's not even plugged in. People have been giving me some feedback about these videos, and they've indicated that I'm not getting a real great pickup on the mic, so I'm going to try to be a little bit more careful about speaking directly to the microphone, and hopefully that fixes some of that problem. So all right, so we're in, this is section 5.5. And of course, this is page 1. We'll keep a running total, and I will do everything I can to have these available to you all. So let's start with this. Let's start with this idea. If we had, let's say that we wanted to look at if there's some way to express this quantity, sine of 2 times an angle, a so-called double angle. Well, we already know how to work with a sum and a difference of angles with regards to sine, and so it's not a crazy notion to say, well, what if the 2 angles we're adding were actually the same angles? So we can make this very algebraic step inside the argument and note that this is sine of a plus a, right? So the double angle, you can write it as a sum, or you can write it as a multiple. Now, from our sum and difference formula, well, in this case, just the sum formula, you'll recall that this is the sine of a sum is equal to the sine of the first angle, which happens to be a, times the cosine of the second angle, which also happens to be A, then plus the sine of the second angle, A, times the cosine of the first angle. Okay, so those are the same term, and so we can combine these into a single expression of, this is just simply 2 times sine of A times cosine of A. And this is really critical, because what we've done with these arguments is we've said, hey, you really have to be careful with what's going on inside this parentheses. You can't just simply drop the 2 out. You know, you can't work inside and outside of these parentheses. And I've alluded to this before. It's because there isn't a homomorphism between the space of the argument and the output of the function. And basically what that means is the operation that happens inside the argument has to be treated separately to the operations that occur outside the argument. And so this may look suspiciously like we're just moving the 2 out, but that's really not what's happening. And if it were the case that you could do that, then trigonometry would be a very, very simple process. It just simply is not as easy as all that. So this is the expression for a double angle, and this is kind of the big result there. This is one of these formulations that you will probably carry with you for the rest of your life. So this one is highly important. So what we're going to separately do is we're going to look at a double angle for cosine, because it actually produces quite a bit different result. And it turns out that the double angle for the cosine function happens to be the secret key, if you will, to producing half angles, to go the other way. Instead of multiplication, actually division. So let's start with the same sort of basic idea. So cosine of 2 times some angle is just simply cosine of the angle plus itself. And then use the sum relationship for cosine A plus B, where A is actually equal to B. We have the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. Now, in each one of those cases, the first angle is the second angle. And notice this doesn't result in a coefficient coming out, but these are the same term, and so we'll write them as a difference of squares. So this is cosine squared of A minus sine squared of A. And this is the so-called first version of the double angle for cosine. Now, what you might have noticed just by looking at this is that we have something that looks an awful lot like a Pythagorean identity. It's not quite the same because we have this minus sign here. But what we can do is we can simplify this expression so it only has a single trig function in it. We can either substitute what cosine squared is equal to, or we can substitute what sine squared is equal to. So I'm going to do the cosine first, which, as you recall, cosine squared is actually equal to 1 minus sine squared. So this is, I'm going to put that into a parentheses there. And that's just a straight out the box, the first Pythagorean identity. And notice that when what we've done is we've created similar terms. We have a minus sine squared here. We also have a minus sine squared here. And so we end up with 1 minus 2 sine squared of A. So this is a second formulation for the cosine of a double angle, which is kind of neat because what we have now is a relationship between cosine of a double angle and sine of the regular angle. And what we're going to do in 5.6 is we're going to actually use this relationship to go backwards and look at half angles. Okay, so this is kind of useful. And now what we're going to do is actually come back to this original expression and do the same thing, except we're going to make a substitution for sine squared as opposed to cosine squared. Okay, so going back from this expression, we have cosine squared of A minus the quantity 1 minus cosine squared of A. This is I'm just substituting for sine squared. Being careful with the SIG in. You'll notice when this distributes, I end up with -1 plus cosine squared. So I actually end up with 2 cosine squared minus 1. And this is the so-called third version for the cosine of a double angle. And again, notice what's going on here. We've got a relationship between a double angle and a formula half of that angle, right? This angle are related by half. I mean, we're calling this the double angle formula, but we could think of this as being, well, this is also somehow telling us something about the half angle as well. So we're learning how to multiply, but we're going to use this expression to divide. Okay, so the next one, I don't think I think I want to do this on another sheet of paper because I don't think I have quite enough space to get the whole thing on there. Okay, so now we're going to be interested in looking at the tangent of a double angle. This one is, I mean, it's not really all that super exciting, but it does come up from time to time. So remember that just like before, we're going to break this out into a sum where it's something times itself. And remember, the sum formulation for tangent A plus B, is that you have the tangent of the first angle plus the tangent of the second angle minus, over 1 minus the product tangent of the first angle times the tangent of the second angle. And since A and B are equal, we're going to get a little bit of simplification that comes out of this. We end up with 2 tangent of A all over 1 minus tangent squared of A. Now there's a real sort of desire to turn that into like a secant or something, and it simply doesn't make it cleaner. It looks an awful lot like a Pythagorean identity, but that SIGN difference really doesn't allow you to make this any simpler than what we've got right here. So this particular expression does not have a whole lot of utility, but it is sort of, for completeness sake, it allows us to, we have the 3 big trig functions, sine, cosine, and tangent. So what I'd like to do, and I don't want to do a whole bunch of this, but I'd like to do maybe just do a quick problem, and then maybe I'll come back and start another video, because I think I've been talking here quite some time. But let's just do a quick example of that kind of reinforces what we already know. This is a direct application of the cosine of a double angle. So let's do this. Let's start with find cosine of 60 degrees. Duh. We know what cosine of 60 degrees is. It's it equals 1/2. But I'm going to use a double angle formula. So how does the double angle work? Well, okay, so what I'm wanting to find is cosine of 60 degrees. Note that is cosine of 2 times 30 degrees. And there's our 2a, right? That's sort of the key. Like, for whatever reason, when you're working with these double double angles, and then also when we work with half angles. For whatever reason, people mess this up all the time. They, instead of writing this as 2 times 30, they'll have some other kind of weird thing. It's pretty easy when there's a number there, but once you start putting some variables in there, it starts to become a little bit confusing. So as I've said previously, just be really, really meticulous about the arithmetic you're doing, because it's easy to lose negative signs. It's easy to multiply when you mean to divide, you know. Anyways, so using the sum formula, I'll just do one. Let's just use sine, right? So the so-called third version that we just, well, second version that we derived, which is that it's 1 minus 2 times the sine squared of whatever the regular angle is. And so here you're seeing 2 times 30, here's 30. So this is clearly a double angle formula. And now I'll just substitute. So I've got 1 minus 2 times the quantity. Well, sine of 30 degrees is 1/2, right? Sine of 30 degrees is 1/2. And don't forget to square it. So when we simplify this expression, this is going to be 1 minus 2 times 1/4, which equals 1 minus 1/2, which happens to equal 1/2. Well, that's good that we get the result that we already knew. But you can see how this is sort of a quick demonstration that the double angle formula does work. I just want to emphasize this again. You can't just simply have these units pop out, right? It looks like somehow that's being replicated, and there are reasons for why that works. But don't make the mistake ever of saying that cosine of 2x is equal to 2 cosine of x. That's not true. And the same thing with sine. Don't make the mistake of saying, well, you know, we could do it with negative signs. We could do some interesting things with negative signs in the argument. They kind of popped out or went away. But when it comes to these multiple, when it comes to these coefficients inside the argument, you can't simply make this adjustment. And that's where I have seen people make persistent mistakes. So don't go down this road. Just realize that anytime you have a double angle, like for example tangent, you have to use this formula. And the same thing's true with sine and cosine. You'll want to memorize those because not necessarily the tangent one. I mean, the tangent one's used, but the sine and the cosine relationships are actually probably the most important, and the ones that are most often employed, because basically what it allows you to do is, in one direction you can turn an argument, a doubling of an argument, into an increase in the power of the function, and then the other way you can decrease the argument, and that's 5.6. You can decrease the power of the argument by doubling the angle. And that turns out to be really, really useful. So not necessarily in this class, but all right. So I'm gonna call it quits here, and I will see you in the next video.